Not to say that at some point you'll have conversations. That's okay. So, all right. So, solving external forces on a truss is the notes for today. We started this last class period. We talked about two different objectives last class period. This one is for the second objective, using equations of equilibrium to calculate unknown external forces on a truss. So we worked out one example last time, which is great, but you're not proficient just yet at solving these. And at some point, we're going to move to internal forces on a truss. So it's important that you understand how to solve the external forces first, because if you cannot solve the external forces first, then there's no point in moving on to the internal because they're all going to be wrong. Okay? Now, the nice thing about this is there's a process. So I'm going to write down some steps, and I think you already have some of those steps in your previous notes. But I'll officially write your steps in order for solving for external forces on a truss. And no matter what truss I give you, you always follow those steps. Step 1, step 2, step 3, step 4. The truss just changes. The dimensions change. The number of members change. Okay? So here I have a truss with, as we zoom in a little bit here, with a total of 5 members. Okay? So this right here is a member. This is member AD. So it goes from joint A to joint D. This is known as a joint A. Okay? It's where the members connect. This is joint B. This is joint C, and this is joint D. Okay, now I mentioned 5 members because we have AD, we have member AB, we have member BC, we have member DC or CD, and we have member DB or BD. So it's like line segments, right? It doesn't matter if you change the letters around, right? The name, it's BD or DB. Okay, so this is a 5-member truss. So when we solve for the external forces on a truss, let me see. One of the first things we'll do is, let me go to write out our steps here. So here are our steps. Now I'm going to use a color that's not yellow because you can't see that. Okay. So step number 1, we're going to draw the free body diagram. Okay. Now, free body diagrams at this point for y'all should be somewhat familiar. We did talk about that already. So on the pre-test, I saw some of you guys had like 9 questions right or 12 questions right. Some of that may just be because of the fact you guessed, right? And you guessed right. But some of it may have been the fact that you actually knew the answer to the question. There were some questions that asked for free body diagrams of trusses. There were some questions that asked about maybe some of the external forces on the truss, and maybe some of you were able to get that based on last class period's lecture. But then there was a lot of stuff you didn't know, and that's okay, because we're going to learn it at some point. So step number 1 for solving the external forces on truss is draw the free body diagram of the truss, okay? And then step number 2 is before we even move forward with calculations of the truss, and this is a step I skipped last time because we really didn't need it. It was automatically assumed that it was what's called statically determinate. Okay? We're going to verify something called static determinacy. You're like, Mr. V, what the heck is that? Okay? So static determinacy is this. It tells you that you can actually solve the truss, that there's enough equations for the number of unknowns that you have. Okay? So the equation for that is pretty straightforward. 2j equals m plus r. You're like, hey, I've seen that before. It was in your pretest today. You remember it, Andrew? Remember seeing that? 2j equals m plus r. Okay? Where j represents the number of joints, m represents the number of members, and r represents the number of potential reaction forces. So the reason we draw our free body diagram first, because it's going to show us our reaction forces Okay? You can zoom in just a little bit more if you need it. So step number 1, we'll draw the free body diagram of the truss. We'll verify static determinacy. Again, that's going to tell us that we can actually solve the truss. The truss is solvable. We're going to have enough equations for the number of unknowns we have. And it gives us some idea of balance and stability on the truss, but not fully. Okay, it really has to do with just the number of equations and the number of unknowns. Okay. Then step number 3 is we're going to then, choose our point of rotation. Okay. Now, here's a hint. Always choose the pin. And as you recall, last class period, I told you why we choose the pin. Okay? Always choose the pin connection or pin support. And then once we get to that point, this is where our equations of equilibrium. So that objective that says use equations of equilibrium to calculate the external forces on a truss. Our equations of equilibrium are the sum of the moments about the pin connection. We're going to set that equal to 0. So we're going to have to generate a moment. So I'll zoom in even more. So you'll have to write out a moment equation. And then our last step is, once we've done with that, we move into the sum of the forces in the x direction and then the sum of the forces in the y direction. Anything going up is positive. And at that point, you should have all your answers for your external forces, and we're done. Okay? So it's very procedural. You'll follow these same steps every single truss I give you. Any questions so far? Okay. Now, like I said, I'm recording a video, so I'll go ahead and place this video on its learning. So if you need to go back and review the notes, you can. It'll be uploaded to YouTube, so it'll be a YouTube link. Okay. I have like 16 followers on YouTube. Let's go. Well, I have 2 YouTube accounts. If I add both of them combined, it's like 25. So I'm not exactly trying to become a YouTube star, but anyway, 25 followers. Yep. Got to start somewhere, right? All right. Okay. So those are our steps. Did everybody capture those? All right. So let's go ahead and move this off to the side. Let me put my pencil down because it's... All right. So we'll start with step number 1. Step number 1. The free body diagram, okay? You have the truss. All right, what do we notice about the truss? It's 2 triangles. Yeah, we talked about how trusses are a system of supports made up of triangles. What else do you notice about the way the truss is set up? Anything? Anybody? What information is given to you, I guess, is another way to ask it. The length of the members. So I see that member AD has a distance of 5 meters. Member AB is 3 meters long. What other information is given? Oh, what was that, Andrew? Yeah, Andrew said what supports do we have. So what supports do we have? We have a pin, so tell me where the pin is at. At D, yeah, absolutely. We have a pin support at D, and we have a roller support at C. Okay? What other information is given to us? Direction of one of the external forces. So we have an applied force here of 100 newtons. Okay? So this 100 Newton force, it's applied at joint B, and it's to the right. Okay, so that's the information we're given. So here's what I want you to do. I want you to work with your neighbor, and I want you to draw the free body diagram of the truss. And then I'll go ahead and call upon somebody in, I don't know, the next 2 minutes. Okay? So go ahead and spend a minute thinking about yourself, then spend the next minute discussing it with your neighbor. All right, go ahead and go. So hopefully with your group, your partner, you came up with something. So when we redraw the truss, I really just said what? What were the steps of drawing a free body diagram for a truss? What did I say? No, we had documented some things that.
Yes, you did.
We documented some things that we assume, right? I think they're on the back of the board still. Right? Our assumptions for truss free body diagrams. We said that all connections are frictionless. We said that all truss members are weightless. And we said that all members are in tension or compression. So you should have that in your notes. Okay, so we're not going to have weight due to gravity on our free body diagram. What I essentially said was redraw the truss just as you see it, but do not draw your supports. So don't draw the pin, don't draw the roller. So back in your original diagram here, you don't draw this little triangle down here at D, and you don't draw the circle. What are we going to do there at those points? Replace them with what? Reaction forces. So drawing a free body diagram of truss is pretty straightforward. All you do is redraw what you see and replace those with reaction forces. Okay? So redraw what you see, replace it with reaction forces. How many reaction forces at joint D? 2. Okay? It is a pin connection, so there are 2. Good job. So let me go ahead and zoom in just a bit. Let me erase. I don't know how that got onto my. We talked about how we always assume positive X and Y directions for our reaction forces. Shh, listen up. All right. So I've got 2 forces, one in the X, one in the Y. Now we give them some names, right? So what is the name? What can I name this reaction force right here that I'm pointing at? FDX or RDX, okay? So we give it a name. If you wanted it to name it FDX, you could. It's a force, right? We just like to use capital R for reaction force. So we have a reaction force at joint D in the X direction. So RDX. And what's the other one called? RDY, reaction force at joint D in the Y direction. Now, again, these directions are assumed. I don't know if RDX is really to the right. I don't know if RDY is really up. We're going to let the physics work it out for us and tell us if our assumptions were correct or not. Okay? And if your assumptions are incorrect, it's not a big deal. It's not that you're wrong. You have to assume something. Okay? The physics lets you know if your direction was right or not. And so at the end of it, you just correct the direction. Okay? So if you get an incorrect assumption, juniors, if you get an incorrect assumption, you're not wrong. You're not going to lose points. Okay? All right. Now, how many reaction forces do I have at C? And what direction is it in? Is it in the X direction or the Y direction? And what is the reasoning? Okay, so, all right, spend 10, 15 seconds deciding the direction and discuss it with your neighbor. So name a direction and then give it a reason why you chose that. Five more seconds. 3, 2, 1. All right. Let's see. Edward, since you've been absent for a couple days, what conversations did you hear around you? What direction was it? Okay, you chose up. And why did y'all choose up? Yeah, in the X direction, it can't support it because if we go back to our original, oopsies. I don't want to move the whole thing. There we go. In our original diagram, we have a roller here. And this roller is going to slide left or right. So it can't support left or right because it slides. But if I push down on the roller pushes back up. So it can support in the Y direction only. So in the free body diagram, that reaction force is in the Y direction, and by convention, we assume positive, so we're going to assume that it pushes up. Now, Edward, did your team or folks around you give it a name? If you were to give it a name, what do you think, based on our previous convention? RCY. Good job. All right. RCY. All right, so there's our free body diagram. There's step 1, okay? Now, we spent a good, probably close to 8 minutes on free body diagram for this truss. In future trusses, it should be like less than 60 seconds, right? Because it's not difficult. All you do is you redraw the truss and replace the pin and the roller with reaction forces. Pin always has 2, roller always has 1. And we always assume positive X and Y directions. The only one that you have to think a little bit more about is the roller. Because it only supports in one direction, you have to decide, is that X or is that Y? And it's based on the orientation of that roller. Okay, how it's set up. So there's step number 1. Okay? So I want you to reflect right now on your own. You don't have to discuss it with a neighbor. Spend 5 seconds thinking, okay, what did I do? Did I understand what we did? And could I do it again? All right? And if you understood what we just did, then you're on your way to solving trusses just fine. Okay? Shh. Guys, I hear a lot of side talking still. All right. Now, again, remember, we want to limit the side talking unless I tell you to discuss it because I am recording, so we don't all want that side talking to come out in the video. Okay, it'll be distracting. All right, so now that we've got step number 1 done, we can move into step number 2, which is verify static determinacy. Static determinacy. And it's going to tell you if the truss is statically determinate, that's the language we use, or statically indeterminate. So I'll write these down so that way you have the academic language. So there's a question mark there, or is it statically indeterminate? Okay? So if a UTRGV engineering professor talks to you and said, hey, what are you doing in POE? You can say, oh, we're verifying static determinacy on a truss, and we're determining if it was statically determinate or statically indeterminate. And they go, holy crap, holy cow, I can't believe a junior in high school knows that language. Okay? Because when I was a junior in high school, I didn't know that language because we didn't solve trusses when I was a junior. Okay? We didn't have POE when I was here. They offered IED for the first time when I was a junior at Science Academy. So I took IED my junior year because they were piloting the class for the first time. Okay? We actually started EDD first because EDD for Project Lead the Way actually started here at Science Academy. Okay? Mr. Colson, who's down the hall, and Mr. Schroll, who is my EDD teacher, wrote the curriculum for EDD for Project Lead the Way. Now, any school that's a Project Lead the Way school in the nation might offer EDD, then it started here. Okay? So at the time, we had EDD and IED. All right, so anyway, that's just some background information that we really don't need for trusses. But anyway, statically determinate or not is the question. So we go back to the equation from our steps that you just wrote down earlier, 2J equals M plus R. We said J was number of what? Joints. How many joints do I have? 4 joints, A, B, C, and D. So we're going to replace that variable with the value, 2 times 4. And M represents number of what? Members. So how many members do I have? I said it earlier. 5. Member AB, from A to B, BC, CD, AD, and DB. Okay, so a total of 5 members, so we replace M with 5. And how many reaction forces did we draw on our free body diagram? Reaction forces, not applied forces, reactions. Yeah, I hear 3. Yeah, we drew 3. RDX, RDY, and RCY, so a total of 3. Okay? So it is a super simple equation that tells you if it's even worth moving on, or it's going to tell you you need to redesign your truss so it's statically determinate. Okay? Statically determinate is what we want. Okay, so I'm going to go ahead and highlight this right here. This is what we want. We want it to be statically determinate, not statically indeterminate. Okay, that means we can solve it and we can move on. So as I work out this problem here, this takes us back to like algebra 1, the very first part where you just substitute numbers in and check if the left side equals the right side. That's all we're doing here. And we see that 8 equals 8. So it is statically determinate. Okay? So the first 2 steps of solving external forces on a truss should be, at some point for you, pretty simple and straightforward. Okay? Redraw the truss, replace the supports with reaction forces, and then based on that information from the free body diagram, check 2J equals M plus R. That's step 1 and step 2. Okay? So at some point, you should be a truss solving machine, and these first 2 steps you could probably get done in under 2 minutes. Okay? All it takes is practice. All right, so now let's move on to step number 3. Step number 3. I said that we're going to choose the point of rotation. So what is the point of rotation that we want to choose here? Point D, okay? Why are we choosing point D? Because it's the pin, all right? So this is where the pin is located. Okay? And I mentioned that the reason we choose the pin, who remembers why? What was the reason? We had a pretty valid reason as choosing the pin. What is that? He's giving me some hand signals here. I'm not quite. I think he's trying to land the plane. Yeah. Yeah. Okay, so here's the reason why, juniors. So if I choose this as my point of rotation, all right, listen. If I choose this as my point of rotation, these 2 forces will not generate moments about this point of rotation because these 2 forces have a distance of 0 to that point D. And as you recall, moment is equal to force times perpendicular distance. And if distance is 0, then the whole term is 0. So RDX and RDY won't cause a moment about that point of rotation of D, which means the only 2 forces that I'll have in my moment equation in this example is RCY and this 100 Newton applied force here, which do have some distance from this point D. So these 2 forces will show up in my moment equation. Okay? So step 4, let's go ahead and generate that moment equation. So step number 4. All right. Step number 4, again, we're going to take the sum of the moments about the pin connection, set it equal to 0, and by convention, anything going counterclockwise, any moment going counterclockwise will be positive. This is our rotational equilibrium equation for our equations of equilibrium. All right. So here's my equation. The sum of the moments about point D is equal to now, if you have this on your paper, which you should, I want you to put your finger right here. Okay? Hold it at D. All right? And I want you to hold your finger here at D and then with another finger push up at RCY. What happens to the truss if you're only holding it here? It rotates which direction? Yeah, so if I hold it here with my finger and I push up at C, the truss is going to want to swing counterclockwise. The truss wants to rotate. Okay? So that force is going to cause a moment because a moment, again, is the turning effect of a force. So if you see that turning effect, that means it's going to generate a moment. So we have RCY generating a moment, but that's only the force portion of my equation, moment equals force times perpendicular distance. So we need a perpendicular distance for RCY to my point D, my point of rotation. So what is that perpendicular distance from that force to point of rotation D? Anybody want to take a guess? 3 meters. Great job. So again, focus on the line of action. Oh, I have lightsabers? What? All right. So focus on the line of action of this force. The line of action is vertical. So to make it a perpendicular distance, I should be looking for a horizontal distance from that line of action. And the horizontal distance from this line of action would be 3 meters right here, okay, to D. So 3 meters. Good job, Aiden. Now, earlier we said that if we hold it at D, whoops. No. If we hold it at D, let me erase that, and push up at RCY, it's going to rotate counterclockwise. So is that a positive or negative moment? It'll be a positive moment, okay? Now the other force that we have that's going to generate rotation about point D, so again, let me choose my other. Hold it right here at D, and use your other fingers to push up here, to push over here. You can even push here and here, but you're going to see when you push at D, nothing happens because I'm holding it at D. But if I push at joint B, to the right, what happens to my truss? It goes, what was that, Gigi? Clockwise rotation. Is clockwise rotation positive or negative? Negative. So this will be minus 100 newtons is my force. And what is the perpendicular distance to point D from that line of action? 5 meters. Good job. Okay? Again, focus on the line of action. The line of action is horizontal. So I want you to focus on the line of action of that force. And you're always measuring the distance from that line of action. Okay? Why is it not the diagonal, this hypotenuse right here? Why is this distance not important? Because it's not horizontal. Why does it have to be horizontal? No, it's not perpendicular. It's not, I gave the answer away. It's not vertical distance, right? Right? Because it's not perpendicular is the answer, right? This distance here is not a perpendicular distance to joint D from this line of action. The perpendicular distance is this 5 meters, and you can see this 90-degree angle right here, okay? So 5 meters is my perpendicular distance. And static equilibrium tells us that the sum of these moments should be equal to 0. So there's my moment equation. RCY times 3 minus 100 times 5. And if you didn't notice in this example, we're working in the metric system. So our forces are in newtons, our distances are meters. Last class period, we worked in the imperial system where our forces were in pounds and our distances were in feet. The process is the same. Siri, no talking in class. I heard Siri. Okay. All right, so go ahead and spend a minute solving for RCY with your neighbor. Go ahead and work. You should be finished up with your conversation at this point. Let me call on Linus. Linus, did you get an answer for RCY?
I did not. I would like to phone a friend.
Phone a friend. All right, who are you going to call on? Shrey, what did you get for RCY? 50? No, we don't. Remember, let's not laugh at each other here.
It's 500 over 3.
Yeah, that's exactly right. So what's 500 over 3? Oh, yeah, that's 1/3 times 500. No, not 20-something. 166.6. Thank you. Okay? 6.7, yes. Okay? All right. So, all right, great job. You can give Shrey a round of applause and Audi. All right? All right, so take a look at the algebra here, okay? So we have 100 newtons times 5 meters. This will combine to Newton meters. Negative 100 times 5 is negative 500 Newton meters. And I'm going to write out all the steps just so you can see it. And I can just put, 3 meters in the front here. Because typically when we write this out, we have the number in front of the variable, right? From algebra class, like 5x. You don't usually write x5, do you? Right, you write 5x, okay? So this is 3 times RCY minus 500 Newton meters equals 0. We're going to go ahead and add the 500 Newton meters to both sides. So we end up with 3 meters RCY on the left equals, remember I'm recording a video. Okay, equals 500 Newton meters. And then my last step is to divide by 3 meters. The 3 meters cancel out on the left, reduce to 1. So I'm left with RCY equals 500 Newton meters divided by 3 meters. What happens to my meters? They're gone. They're reduced to 1. So I have newtons as my final answer, which makes sense because RCY is a force. So RCY equals 500 divided by 3, which is 166.67 newtons. My answer is positive. So what does that tell me about my assumption for RCY earlier? It was a correct assumption. I assumed that RCY was up because I said that's just the process we follow. We're always going to assume positive directions. So we assume positive Y, and the physics said, dudette, you're right. Okay, it was up, 166.67. Okay, so there's step 4 of solving for external forces on a truss. Okay, this is probably by far the hardest step of this process, is generating that moment equation. The other day in class, I went ahead and showed you another way to generate the equation using a table, and I believe that is still up here on this board, if I'm not mistaken. If I lied, it's an entirely different problem. But you should have it in your notes, okay? Almost out of time here in class. Step number 5. Shh. Guys, I'm recording again. Sum of forces in the x direction equals 0. Sum of forces in the y direction equals 0. Anything to the right is positive for x. Anything going up is positive for y. So those are our conventions. So this free body diagram, we always go back to it for these steps, step 4 and step 5. We go back to our free body diagram. Okay, and I mentioned in this class the free body diagram is going to look a little bit different compared to the free body diagrams you've done in physics, because in physics your free body diagrams are like, you know, a square or a circle or a rectangle. Okay, you typically don't have dimensions and all these different points of where the forces are applied on your free body diagrams in physics class. Okay, but a lot of what we do here you've seen in physics. Okay, it's just a matter of taking that knowledge and transferring it over here with a little bit of additional information and knowledge. So here I have the sum of forces in the x direction. I'll start with that equation. Anything to the right is positive. I go up to my free body diagram and I say, Mr. V, I wonder which forces are in the x direction. I look at my free body diagram and I start identifying them. Okay? So let me call on Fleming. Richard Fleming. How many forces are in the x direction? Look at your free body diagram. 2. Can you name them? Why not? They're up on the free body diagram. Come on, let's go. We're running out of time. RDX and what else? And it may not have a name. It may already have a magnitude.
I don't know.
All right, someone help Fleming out. 100 newtons, okay? So we said by convention anything to the right is positive. So what can I say about those two forces? They're both positive. Good job. Okay? So I have RDX to the right. So that'll be positive force plus 100 newtons to the right. They're both to the right, so they're going to combine. But static equilibrium tells us that this should all equal what? 0. So what does that tell me about RDX then? It's negative what? Negative 100 newtons. Good job, guys. Okay? Equals negative 100 newtons. And what does this tell me then? It goes the other way. Good job, Jacob. My assumption of RDX going to the right was incorrect. Okay? And again, you're going to have to be okay with that. Some of you are like, how do I always be right? Okay? Well, you just think about it a little more then. Okay? So if you want to always be right, assume the opposite. But I want you to follow a process so that we're all on the same page. And if you go against the process, it's okay. But you'll have to realize that the negative always means that it's the opposite of your assumption. So if you assume to the left and it's negative at the end of the physics, that tells you your assumption's wrong. So it's really to the right. Okay? Here, the positives and negatives will at least line up with our conventions that you're used to. So if we assume right and it's negative, that means it's left. So RDX is really to the left. Now let's finish off step number 5 quickly. Sum of forces in the y direction. I want you to spend 2 minutes discussing this equation with your neighbor, set it up, and give me a solution for what's missing. Okay? So solve for the unknown. Fleming, put your phone away, you're going to lose it. All right? You should be focused on the notes. You should be having some academic discourse with your neighbor. And your phones only get in the way of that. Let me pause this so can someone read out to me the equation here? No, the equation. Oh, sorry, that was not an answer. Thank you, Gigi. Gigi, say it again. Hold on, don't leave yet. 166.67 plus RDY. So what does RDY equal to? Yep, negative 166. So our assumption was wrong. It goes the other way. All right, so this equation came from RDY plus RCY, which we know is 166.67. And those are the only two forces in the y direction, so that has to sum up to 0. So solving for RDY, we end up with negative 166.67, which tells us our assumption for RDY going up is incorrect. It's actually going the opposite way.